We have a mechanism. I'm not going to show the mechanism, but we could go through a variety of mechanistic steps. Whoops. And you should have gotten it to come down to either the enolate form, which I'm going to redraw that. I'm going to draw that as the enol form, or the enolate form. We got a hydrogen out there, right? Same deal on the other side, right? How did we know which hydrogen to pick? Okay, it's highlighted, so there's your easy answer. Okay, the next part is I heard an alpha. Okay, so we could reference the alpha position. What else could we reference? There's a little unhappy gorilla there. Anybody see a little unhappy gorilla? So we have what we might reference as our acidic, our basic, it's our red and blue. Why would we pick those hydrogens? How do you know they're the most acidic?
The rules.
The rules. How do you apply the rules? You would have to know the rules, meaning you have to draw out each of the structures, removing each hydrogen and saying, how does this compare to the other hydrogen lost? Okay? For those of you saying, well, I don't want to do all that work, your memory is going to have to get really, really, really good. Okay? You need to start applying and saying, what happens if I remove a hydrogen here? Does this have some kind of stabilization? Okay? For the first case, why did I remove the red hydrogens and not now that purple hydrogen?
Is it the greater number of resonance structures from one to the other?
The red hydrogens would be able to donate the negative charge both directions. The purple hydrogen can only donate that charge in one position. So there's more resonance, okay, for removing the red hydrogens. In the other structure, what about that purple hydrogen? Why did we not remove that one? Isn't it closer to the electronegative element?
Is it
Doesn't donate.
because when you do the conjugate base?
When you draw the conjugate base and put the negative charge on that carbon, can we do anything with it? No. There is no resonance stabilization. So inductively, it may be more acidic, but the red hydrogen has a resonance contributor, which makes it more acidic when it is removed.
Could you also say it's in the vanillic position?
You can reference the vanillic position. It's not really a vanillic because it's a carbonyl, not an alkene, and I don't know how to name that, so don't ask. Really what you should remember is the aldehyde hydrogen is not acidic. Okay? If you just remember that, that's one of those things that makes it easier. The Y is looking at all your resonance. Okay? So we have these two systems. We can get to our acidic or basic, or get to our enolate form, either under acidic or basic conditions. But now the next question is, which one of those has a higher concentration of the enol or enolate? Okay. Let's phrase that again. We have structure A and we have structure B. Which one of those two makes more of the enol enolate? Why does A make more of the enol enolate?
There's 2 oxygens to work with.
Why does 2 oxygens matter?
Resonance.
More resonance. Really what we're going back to? The hydrogens in A are more acidic than the hydrogens in B. Okay? Which means that initial step of removing the hydrogen, or secondary step of removing that hydrogen, depending on which mechanism, is easier. How could we identify that ahead of time instead of trying to think about it slowly like we just did? You could look at the pKa's. Okay? The pKa for our structure A is a pKa of 9. The pKa for the other one is a pKa of 16.7. Okay? Meaning, our leftmost structure is more acidic. It is more likely to go through and form the enolate, okay, faster. Why is that important to us? Well, if I'm trying to just make the enol or enolate, which of these structures should I start with? All I want is an enol or an enolate. Which of those two materials would I choose as my starting material? A. Why? It makes more. Okay. There's another reason why we could pick A. Okay, it goes faster, partly because of the charge. Okay, let's say we want to do it under basic conditions. Why would I want A over B? If A is more acidic, what does that mean about the base that I can use? It could be weaker. I can use a weaker base because A is already more acidic. I don't have to use as strong a base. Well, why do I care about that? Do I want my face to melt off in lab? No. So I can use a weaker base, thereby putting less toxins into the world. We can go through this big, fun green chemistry feel behind it. Okay? We're being safer within this. Which then brings up the point of looking at what bases we can use. Okay? We've seen our standard bases, the oxides, or hydroxide, ethoxide, methoxide. Okay? So in this case, we have ethoxide. Okay? That's a good, strong base. Why is it a strong base? It is charged negative. Negative charge. Next one, hydride. Charged, so we say that's a strong base. Last one, amide. We can run into issues on naming later. Also charged. So those are all strong bases. Are they all equally strong? Why not?
What they're attached to. Size.
So what they're connected to, I heard size. What do you mean size? Because I think that's going to get where we want it to be. Our rules. Charge was the first thing we look at. The next thing we look at?
Size.
Size. What can you tell me about the size of the atom holding the charge? Oxygen versus nitrogen, roughly the same. What about hydrogen? It's super, super small. What does that mean about its reactivity as a negative? Very, very reactive, which would suggest the hydride is the strongest base of these three. Okay? Between the oxygen and the nitrogen, because they're in the same row, size is almost identical. So size doesn't help us. What should we move to?
Electronegativity.
Electronegativity. What can you tell me about the electronegativity between oxygen and nitrogen? Oxygen is more electronegative, which means? It is a worse base. Okay, it becomes less reactive. Why?
It's holding onto those electrons.
By being electronegative, it's holding the electrons, not sharing them, which is what it necessarily needs to do to act as a base. So amide ends up being our next strongest base, and the one that we've memorized as a strong base, our oxide, ends up being the weakest of our strong bases. Okay? What can we do further within this? What can ethoxide act as? There's a really easy answer jumping right out of the page at you. It's a base. Okay, what else could it act as? A nucleophile. What does that mean about choosing ethoxide as a decent base? Probably not the best idea because it could also act as a nucleophile. We could get two reactions. Why can it act as a nucleophile? Relatively small. Okay. So if we jump to the amide, that negative charge, we've still got a base. Can it act as a nucleophile? Why is this one not acting as a nucleophile? Okay. This is too large to act as a nucleophile. Okay. Which then brings up the fun one, hydride. We definitely still have that base characteristic. What do you think? Okay. Just because it's strong doesn't mean it's a nucleophile. The amide was stronger than our oxide, and that's not a nucleophile. No. What it would break would be the pi bond. It's small, right? What did we say ethoxide could act as? A nucleophile because small. So we might think hydride being small should act as a nucleophile. And of course we're wrong.
Probably too strong of a base to even try and do that. It grabs the hydrogen before it does something.
Okay. So we've got a couple things going on here. One, it is an exceptionally strong base because of how small it is, which means it is very, very reactive. But because it's small, it could theoretically make it inside, and yet somehow it doesn't. This one, I think, is very counterintuitive. Hydride is actually massive. It is so reactive in the bond that it's being put in as, it's usually going in as, say, sodium hydride. That bond is so ionic that what happens to its solubility? It's insoluble. Well, if it never dissolves, the only place where the hydride can react is on the surface of the solid. We have a very small surface area in comparison to if it entirely dissolved. Sodium hydride is probably the worst nucleophile because it is so bloody reactive as a reagent, okay, that it does not dissolve well, and that keeps it acting solely as a base. So it is bizarrely one of the bulkiest bases we could possibly use. Okay. Next thing to kind of evaluate, or actually we have questions on that. Okay, the next thing that we could evaluate within these, what do we notice is different between all of those reactions? It's actually not all of them. But I would say this one has a difference.
Have an equilibrium.
For some reason, when we use ethoxide, we'll notice that the reaction arrow is not solely going to the products. In fact, that reaction arrow says that we primarily keep our reactants. Okay, why would we primarily keep our reactants? What did we say was the reactivity of this one? Not very reactive in comparison to our previous slide. Okay. So why, when I moved the other ones, do I get it to react?
Because the negative carbon is a stronger base than the negative ethylic side.
We need to start comparing our reactive species across the reaction arrow. I'm looking at a negative oxygen versus negative carbon. Which is more stable? Oxygen, which would suggest stays towards the oxygen side. Hydride versus carbon, which is more stable? Carbon, which way does the reaction favor? Shifts towards the carbon.
Would you also say that on that one you're giving off a gas?
We'll come back to that. Nitrogen versus our oxygen. This one gets trickier. We might still lean towards the nitrogen. Okay. Why do we see some favoring towards that product? Resonance suggesting that our negative charge is actually held where? On the oxygen, which is more stable. Oxygen or negative nitrogen? Negative oxygen. Products are favored. Okay. So we have to be thinking of these pieces and how they can get in the way and how they can alter our reaction. Okay. We've got one more big point brought up with that middle reaction. You'll notice that they're saying minus H2 gas. Okay. Why is that reaction more than any of the others favoring only the products?
It can't go back because the gas is gone.
To reverse the reaction, what has to happen?
Get more H2.
Base must pick up the hydrogen. Well, that works. What does that react with? Okay, at best, it would be reacting with HH, RH2, but what's the issue with H2? It's a gas, and what does the gas do? Bubbles out of the solution, and we don't have it to react. If it's no longer present, can we reverse the reaction? No. Okay, so we need to be thinking not only of our enolates, but then also what base we're using to run that reaction. Okay, so we could go through and look at pKa's. Those are kind of fun. Anybody like quantifying things? Yeah, I didn't think so. Okay. The next thing to get at with our enolates. What is special about this carbonyl compound in comparison to the ones we've been looking at? What about the location of the pi bond?
You have one that's in the, more substitutes.
I form the enolate where I form the more substituted double bond, or I form the enol where it's the least substituted. Okay. What does that mean?
Kinetic versus thermodynamic.
I have a kinetic versus a thermodynamic product. Which one's the thermodynamic?
The one that's fast.
What's that?
That's the bottom.
The bottom one, because
It's more stable.
what's more stable?
Alkene.
The alkene is more substituted. We're looking at our thermodynamic product. This necessarily means the top one is our kinetic product. And our thermodynamic versus kinetic arguments, we could go back to our butadiene, and we could look at our intermediates, which really our intermediates were a cheat in that case to see the difference between our kinetic versus thermodynamics. Because where do we see the difference between kinetic and thermodynamic? How do we tell the difference between kinetic and thermodynamic? Where does that difference pop up when we're looking at a reaction? In the transition state. So if we looked at our butadiene and looked at the intermediate's not a transition state. Okay, so we cheated by using the intermediate there. Okay, and we got lucky that it happened to work. When we're looking at our enolates, we really need to be looking not at our intermediates. We need to be looking and thinking about our transition states and how those can affect. Okay? So, we're going to be looking at that first step and the transition state for that. What has to happen? To do that very first step, what has to happen? We have to have some base come in and remove a hydrogen. Which of those two steps do you think is easier to do?
Second, the purple.
Ooh, different answers. I like that. Why the purple one?
Tertiary carbocations.
You're saying you're forming the more stable carbocation. Well, we got a problem there. It's not a carbocation. It's actually a carbanion. Okay, so I'll call out issues with that. Does that change your interpretation? Okay. How does that change your interpretation?
Carbanion must be least substituted.
Carbanion wants to be least substituted. I might predict the top one to be a little bit better off. Okay. What else could we evaluate to help us decide what's going on with that transition state? Because really what you told me is the bottom one goes faster because the product is more stable. Can't do that. We're looking at the transition state. The product's not there yet.
You can also look at resonance.
Depends how high it has to go.
Okay, but why is it going high? What has to happen in that transition state? Where is our transition state? What is happening? The hydrogen's being removed by the base. What is the base? A source of electrons. Okay. Which of those two is going to have a higher transition state? As in we have more electrons near the same point. The bottom one. It's more substituted, meaning more electrons get in the same space, which necessarily does what to that energy? Kicks it higher. What happens to the red one? It's lower. Our red one and freaking color coding. Our top one ends up being our kinetic product out of that. Let me just pretend I didn't color code that.
We knew what you meant.
Okay? How could we favor one product over the other?
Heat.
Okay? We could try and throw heat into the situation. How is that going to impact us? If we add more energy, what's going to happen? We're going to have the energy to clear the activation barrier, all activation barriers, and we're going to favor the thermodynamic. Why would we favor the thermodynamic over the kinetic? It's more stable, it's lower in energy, which then means what happens when I form the thermodynamic product? It stays there. It cannot reverse. While the kinetic product is forming first and quickest out of this reaction, I've provided enough heat that what does the kinetic product do? It reverses back to the starting material. And because the thermodynamic is now constantly removing reactant and an irreversible process, okay, we have to push our kind of di-equilibrium, bi-equilibrium system where we end up losing our kinetic product. Okay. How could we force the kinetic product instead of the thermodynamic then?
Make it cold.
Make it cold. If it's cold, there's now no longer enough energy to reverse either the kinetic or the thermodynamic product, and we only form the one that formed first, which is our kinetic. Okay, cool. So we could use temperature. The issue with temperature is it's not the easiest to manipulate, and sometimes it works well, sometimes it doesn't. What else could we do? Change the type of base. Okay. So let's pick a base.
H minus.
Okay, H minus. What happens when H minus as a base is added? What's the first product formed? Okay. Maybe a difficult question because you're trying to, I don't know which one's which. The first product is always this product. It is never different. It is always the kinetic because lower activation energy. It's a faster reaction. We always form the kinetic product first. If we use sodium hydride, what did we say was the issue with sodium hydride? It's an irreversible reaction, which then means all I can get is the kinetic. I cannot make any other product because that reaction can't reverse. What if I use sodium hydroxide? Which product do I get first? The kinetic. But what's the issue with sodium hydroxide? It is a reversible reaction. So while I may be forming the kinetic first, it reverses back to the starting material. And as long as there's enough energy, what happens to that starting material? Some of the time, it makes it to the thermodynamic. Can I reverse the thermodynamic? No. Okay? So we've got reversibility popping up in two cases. Okay? We're referring to the kinetic as a reversible reaction and the thermodynamic as an irreversible reaction. We also have reference to our bases as being reversible and irreversible. If the base is irreversible, which product do we get? The kinetic. Why is that confusing? What did we say the kinetic product was? The reversible one. Okay? So you have to be very careful in your phrasing to make sure what you're looking at. Are we looking at the strength of the base as being reversible or irreversible? Which product do we get? Or are we looking at our products, kinetic or thermodynamic, and evaluating their reversibility? They are all interrelated, but they are easy to get overlapped and confused. Okay? Which is clearly obvious because we're getting some kind of confused looks. Okay? It's also why there's multiple videos on this. So here's a group quiz that I didn't bring any paper for, so I'll just go through and mark attendance for it. Okay. Build an energy diagram for the kinetic or thermodynamic product. Provide the conditions necessary to make yours the major product. So I don't care which one of those two, and that's a lie. Right side of the classroom is going to do the top product. Left side of the classroom is going to do the bottom product. Because we've got tons of whiteboards and the whiteboards are on opposite sides, we'll even turn it into a race. I want to see the energy diagram, left and right. first group to turn it in or submit, draw it correct, will get an extra point on the quiz.
Alright, you guys figured it out.
You have one intermediate. And we have a kinetic product.
We're doing the whole thing.
No, we just have to show the kinetic one.
Oh, I have to draw this?
Well, kinetic will be up here, though.
This starting material needs to be dissolved.
Let's do this. Alright, so.
Whether you can put the right conditions necessary to make yours a major product. What's conditions? We use sodium hydrate, you said, right?
Yeah, so it should be higher. And then low. Correct. We need
I just feel like our.
Heat. No, thermodynamics. Heat.
Well, it doesn't matter, we don't want ours to reverse.
What about for?
We don't care about thermodynamics.
So we want some more base to the one use. So you want to just do the strong base and.
Is that or?
So we add additional sodium.
No, sorry.
So when we do this, can we get
All the way
this stuff?
Do you want to draw the intermediate?
The Y. No, the
Yeah,
line.
you mean- and then it
The
can-
line.
Sure.
Yeah.
When you use this
No,
base.
So we have like a.
We don't want it to be your right way.
All the way to the left.
You're talking this way?
Yeah.
Okay.
I feel like we need that.
Okay.
I'm not sure I understand what we're missing.
I didn't say you were missing anything.
Alright. We win.
Intermediate there.
Do we have an intermediate?
Yeah.
I guess we do.
Or intermediate. You know,
But do we have like the?
So what do you think? Finalize in 10 seconds?
Show the
I
next.
think that's okay.
Well, do we have another activation energy for the? It's not necessary to me, so.
I think that was 10 seconds. Let's take a look at it, see what we think.
No, it's not gonna be a transition.
So there's kind of a flaw in the question, so I think I'm just going to give everybody the extra point. Oh, what's the flaw in the question?
There's.
So knowing what to compare it to would be really, really helpful. How do we know that what you drew is different from what you drew?
It's not quantitative.
Yeah, it's not really quantitative, so it would be nice if they were drawn on the same figure. Okay, so that's a big first thing. What conditions did you run in?
Heat.
Heat, is that it? And base. What can you tell me about the base? Okay, it's a reversible strong base. What did you guys do? Cold and irreversible strong base. So that's good. You're at least counter to each other. I like that. And I think I might be recording. Awkward silence over here. That's pretty awesome. Yep. It's shown up a couple times. So what we've got up here is a big smattering of all of the potential reactions that we can see within this chapter, or will see eventually when looking at our keto and enol forms. Okay? A large portion of these, for instance, the bottom section, actually no, that's a lie. The bottom section is all chapter 18, tail end of chapter 18. Very, very repetitive, and it's probably one of my least favorites because we'll notice that we see Claisen, Diekman, we'll hear Michael, we'll hear a few other names. I find it irritating because it's all going back to the same chemistry. Make an enolate, have it act as a nucleophile. That's it. Okay. But if you make that electrophile that it's reacting with be, say, an aldehyde versus a ketone versus an ester versus an ester that has a really long carbon chain connecting it, somebody rubber stamped their name to the top of it, and we now refer to it by that chemical name or that person's scientist name. It's the same chemistry again and again and again and again. Okay. The top two we've already seen. Okay. We just did it with our symmetric carbonyls or symmetric enolates. And by already seen, we haven't seen all of that section yet. Okay, that's the next unit. So, do you guys want to take a swing at some practice? Okay. Just because of time, this is a nice, I like this question a lot. Actually, though it is technically a little bit more advanced than what you've seen so far. PBr3, you should remember from the last unit, we'll do a substitution. OH exchanges for one of the bromines on the PBr3, and we end up with the acyl bromide. Br2, as Jen was pointing out, under acidic conditions, okay, will convert or take a carbonyl through its enolate chemistry, and it will exchange that hydrogen for bromine. Okay. The black arrow is the one that you officially don't know quite yet, but you might have been able to predict, or didn't predict. Wouldn't actually ask it on a test because of this. The water attacks the acyl chloride, or acyl bromide, kicks out that bromine, and we've got our final product. This is known as we looked up, Helmholtz-Zielinski reaction, which was found on the previous slide that summarized all the reactions. Okay. The next one, our H+, takes us through to the enolate. Because we're running under acidic conditions, where will the enolate form, or the enol form? It's going to form the more stable. Okay. Br2 will react with our enol to make or do our final substitution, or the last part of that. Put our bromine on. Last one, pyridine. Pyridine, we draw out its structure here, which I'm probably going to screw up, but I think I've got it right. Pyridine is special because of the nitrogen with the electrons, and the steric bulk means that this acts almost exclusively as a base. I wish I had a good leaving group.
Oh, you do.
Oh, fascinating. And I get the elimination. And I'd have the final product there. That last one, you're responsible for beginning to end. You, in theory, know every single step of that. Okay. The first one, the black part, you don't know yet. Okay?
Oh, we should already know.
You should already know everything in the bottom one. Okay. That's your enol chemistry. That's your enol acting as a nucleophile with bromine as an electrophile chemistry. That's a standard elimination from first semester. Okay. So chapter 17, we've got the general mechanism idea, which I posted as a video, and it also goes into looking at CA, which is the tail end of the chapter, our conjugate additions. Okay, so I'm going to reserve most of the general mechanism idea and the conjugate addition for that video. So we're just kind of going straight into the reactions. And I would also mention that that video also discusses the difference in reactivity of our carbonyls. Okay. That is the play pause it second video in the link that we just showed. The rest of that chapter is what we'll be talking about in class. Okay? Which means almost. Aldehydes and ketones, they're cool. Look at all this fun stuff that can be an aldehyde or a ketone. Just so you know. I add that because some people like to know where they're going, why things are interesting. I prefer that I just think it's interesting. Like, I don't care that I can make something out of Legos. I just care that I can make something with Legos. But here's your make something. That's your end point of your Legos. Those are the directions. Okay. Nomenclature for aldehydes and ketones. Remember, you are responsible for these. You guys want to take a swing at naming one of these? Or do you think you got it? 5, 4, 3, 2, 1. Looks like you're all trying to name one, so I'll give you a second. Questions about how we put that together?
The hydroxy is only used when the alcohol isn't being made.
So you'll notice the first thing I wrote down was all because an OH means alcohol, so I would put in all. Okay. The ene, you'll notice I just left as an EN. I didn't actually show the ending. Why did I ignore the ending on the alkene? Because I already knew I had 2 higher priority functional groups. Okay. So the ene, I immediately, instincts dropped out. The al and the all, you'll notice I drew them as al and all right away, both of them first, and that's where I run into a problem. Because those are the suffix, that's the ending of the name. Okay? I can't have 2 endings of the name. That goes back to the priorities of our functional groups. The aldehyde is a higher priority than the alcohol, so the alcohol must become a hydroxy. It's then a question of numbering out the chain. The chain is going to be the longest chain that contains the aldehyde. Okay? We've got that numbered out, which gets me the het. 6 for the alkene. I have to specify the location of the ene. And 1 for the aldehyde. Why is the 1 not necessary for the aldehyde? The aldehyde will always be at position 1. Okay? Or at the very end of your chain. Okay? And I'm not sure on that one. You might even be able to imply it being at the end of the chain, but I'm not positive on that. Okay? Then we have the methyl and the hydroxy locating them. Hydroxy comes before methyl because alphabet. Yes?
If the aldehyde was at the end of the chain, then there'd be a higher functional group attached to that structure. So that means
You'd have 2 aldehydes. So I was saying if we dropped a second aldehyde on there, for lack of a better description, we'll just work with this one. I'm not positive on this, but I think you could call that 1, 2, 3, 4, 5, 6 hexandiol without actually specifying the number where the aldehydes are located, because by definition it's going to be 1 and 6. I'm not positive on that 6 though. You might have to. Okay? So nomenclature, excuse me, it's just practice. Keep going through it, keep working it. That's about all I got. I'll try and keep throwing those things in there. A little bit more specific than the video, where's the chemistry of our carbonyl? Okay, we see lone pairs on the oxygen, which would suggest, say that a little bit louder. We have a nucleophilic potential and, probably more importantly, a base potential. Okay, the nucleophilic potential is actually very, very weak. Why? Oxygen is electronegative. Pi is our symbol for electronegativity, or what looks like just a normal X, but that's a Greek letter X. Okay. So the oxygen does not act as a particularly good nucleophile. It can be forced to when put in conditions of a strong enough electrophile, but for the most part, it's not going to do it. Okay. Troy, I think you suggested another thing for reactivity. The carbon is electrophilic. Most of this chapter is going to be centered on the carbon being electrophilic. Okay. We'll ignore pretty much all other chemistry. The oxygen we said could act as a base. Why would we ignore that chemistry in this chapter? This chapter was, come back here, Never mind, I thought it was there, but I didn't. Yeah, it kind of is. We're looking at hydride. What can you tell me about hydride? H minus. Which is a stronger base, H minus or O minus? Or even O? H minus. So I'm not going to look at oxygen being an acid because it's in a really highly negative environment. The next one, carbon nucleophiles. Okay, well that's a little bit better. Can I put an acid in a carbon nucleophile environment? No. Okay. And that's really all that happens within this chapter is carbon and hydrogen nucleophiles. We cannot add an acid to this environment because that would neutralize our nucleophiles. Okay, what I think I'm remembering is that. Yeah, there it is. Chapter 17 is about our strong nucleophiles. If I have a strong nucleophile, can I have the oxygen act as a base? No. Okay? Those reagents would be counter to each other. I wouldn't be able to supply anything to make that oxygen act as a base. When we move into chapter 18, the weak nucleophiles, then yes, absolutely, we'll see the base characteristic of the oxygen.
Question though.
Yes?
If we do add, say, the hydride, couldn't you then force the oxygen to become more basic?
One of the things that we will see is that as we run any of these reactions, that does change the structure. We would end up forming, with our nucleophile attached, now what can you tell me about the oxygen? Yeah, it's charged. Keep going. It is more basic because it's negatively charged. It could also potentially act as a nucleophile at this stage. Okay? Typically, we'll just have it act as a base, pick up a hydrogen. Okay? So yes, once it reacts, we then activate the chemistry of our oxygen. But until it reacts, we got nothing. Okay? Interesting feature within this. We're referencing the carbonyl acting as an electrophile. When was the last time we talked about pi bonds? Of what functional group? Corey was looking at it for help in the synthesis. All right. Bus, meet Corey. Alkenes. What did the alkene act as? A nucleophile. When we take a pi bond and now change one of those atoms from being a similarly electronegative element to a now highly electronegative element, what happened to the reactivity of the pi bond? It's now no longer a good nucleophile. And instead we see the structure acting as an electrophile. Why? Resonance. That's why. Okay? So, here's our spider diagram of everything chapter 17. I believe it's everything chapter 17. Okay, you are responsible for each and every single one of these. Notice at the heart of this, what are we focusing on? A carbonyl. Interestingly enough, not looking at the enol yet. Okay, and that's because the enol classifies as a weak nucleophile, not as a strong one. Okay? And you'll notice that I've also drawn in the resonance. Why draw in the resonance? That allows me to see where the positives and negatives are so I can start to predict the reaction. Okay? The top part is all kind of our straightforward reactions with one caveat. The Wittig, I don't think is straightforward at all. I think it's confusing as all hell, but it's kind of neat. The rest of them are all straightforward. We take a nucleophile and we attack the carbon, which is our electrophile. Okay? We've seen some of that chemistry before. Some of it is new. Okay? The last part of this chapter, which is kind of in a weird, awkward part, if we modify the carbonyl and make it conjugated, okay, it's called an alpha-beta unsaturated carbonyl. Why is it called an alpha-beta unsaturated carbonyl? Well, the carbonyl is the root. What is the very first location after the carbonyl? Alpha. What is the next carbon? Beta. What do we see between the alpha and beta positions? A pi bond, which is a source of unsaturation. Okay, so that's the breakdown of that name. If we conjugate those two near each other, does that change the chemistry of either of those functional groups? Yep. We end up introducing a second electrophilic position, and depending under our conditions, we end up substituting or doing the nucleophilic addition either at our carbon of the alkene or at the carbon of the carbonyl. Tricky chemistry that is all going to come back to kinetics and thermodynamics. Okay, so hydrogen nucleophiles. Okay, how could it possibly react?
Like, as a base?
Yeah, hydride. We just saw that, sodium hydride. That could act as a base. Okay, so it could go through as a base situation. Okay, what was special about it acting as a base? I said NaH. It was irreversible. Yeah. What else did we say was special about NaH?
Huge.
It was huge, meaning
Only after.
not as a nucleophile. It can only act as a base. And yet the heading of this title is hydrogen nucleophiles. So what am I going to have to do almost immediately when I'm looking at the hydrogen or hydride nucleophile? I need to come up with some way to stabilize the hydride nucleophile so that it can exist for long enough to act as a nucleophile. Hydride is so reactive that it will act exclusively as a base. So something else must be put in there to say, here, let's hold on to those electrons ever so slightly, long enough that I can then dump those electrons as a nucleophile. Okay. Have we seen a reagent do that before? Yeah, we have. What reagent did that?
Well, I know we saw it in the lab where we had the OH actually act as a leaving group because there's a highly basic environment.
So where was the hydride nucleophile?
There wasn't a nucleophile. We found something where it acted counterintuitively,
Okay, so counterintuitive. Okay.
but it wasn't.
I want hydride acting as a nucleophile, though. Have we seen it before? As a hint, that in red is setting you up for the circumstance under which hydride acted as a nucleophile before. BH3. What happened when we did BH3? Boron went to the, Boron went to the least substituted position, and what went to the other position? Hydrogen. That hydrogen came in as what charge? Negative. There's a hydrogen nucleophile. Our BH3 reagent did supply hydride. Okay. Why could it supply hydride? What was partially positive? The boron was partially positive because we could reference it as being less electronegative than hydrogen. There's another big feature of the boron that helped us out in this case. If we look at its Lewis structure, which involves valence electrons, what does boron have left over?
Electrons.
No, it does not have electrons left over. It has less than its octet. It has an empty p orbital. What could we put in that empty p orbital? The electrons from our alkene. That then destabilized the boron, and what did the boron do? Kicked off the hydride. The hydride was so reactive that it dumps the hydride back on the structure. We went through that pseudo-cyclic intermediate, which Brian probably attempted to show, but then didn't understand what I was trying to discuss within it. Our four-membered ring for our electrophilic addition. We had a hydride nucleophile as soon as boron had 4 bonds. Okay. Well, if I want it to react with a carbonyl, oh, I didn't quite mean to do that. We could theoretically try and do the same thing with our boron. Okay, but this time it doesn't work very well. Okay, the hydride is not polar enough to initiate this reaction to facilitate it to work. So we need a stronger hydride. How can I get a stronger hydride?
Have a less electronegative center.
Add more hydrogens. What do we end up with? That's an eraser. BH4 minus, and we have sodium borohydride. Where did we see that show up? You're like, stop telling me what I already know, right? Because you already knew this all. What happened in this case? I keep doing that. Oh no, I did that right. No, I didn't. God, freaking stereochemistry. Regiochemistry. When have we seen this reagent pop up? What was that? Also our electrophilic additions, the addition of hydrogen and oxygen across our alkene. Yet another source of hydride as a nucleophile. Okay. Why did we add it as a negative hydride there? We needed a stronger nucleophile to kick off the mercury. Same deal again. Okay. The reagents we're going to end up seeing for our hydride, sodium borohydride, that's our big standard go-to. That's a great hydride nucleophile. The other one that's going to see pop up is lithium aluminum hydride, or LiAl, or typically abbreviated LAH, lithium aluminum hydride. We will end on that note. Think about those differences. We'll actually start Wednesday with a little quiz on what those differences are. So think about them, come up with an explanation for why they might react differently.